back to the Teachers as Scholars. I think this is the cryptography class. I'm not even going to try to say the title. So the goal for this morning is to understand why RSA works. Now, when I teach abstract algebra, one of the motivations I use for a lot of the material covered is RSA encryption. And for years, this was the gold standard on how to encrypt things. So we explained the mechanics of how you do it last time. We did not explain at all why it works. And we did some mathematical preliminaries. So we talked about the Euclidean algorithm and finding the greatest common divisor. What I want to do now is I want to do a few more mathematical preliminaries. A lot of this becomes very easy if you take an advanced undergraduate class in group theory or abstract algebra. And so, well, you've got lunchtime. You know, put the video on like triple play or whatever. No, okay. So we're not going to do an entire class in group theory and abstract algebra. So what I want to do is take the small little bits that I need from this class and prove just what we need for RSA. So what this means is I am not going to be proving statements in the greatest generality possible. With just a little bit more work, we could often prove a lot more than I'm doing. I am trying to do just enough for the application. I will say a few things about how some of this stuff generalizes, and if you're familiar with this, then you can prove a lot of these things a little bit easier. But there are some backdoor tricks we can do where we do not need the full general statement, and we can just argue that for the case we're looking at, this is sufficient. If you want to then generalize, we're in trouble. But for RSA, this will suffice. Okay. So the first thing we're going to do is Fermat's little theorem. So it is not as famous as Fermat's last theorem. It is often abbreviated F lowercase lt to compare with Fermat's last theorem, which is a capital L. And what this says is the following. So consider the set 1, 2, 3, ... n minus 1, where I'll assume n is at least 2. Let phi of n equal the number of elements above relatively prime to n. So let's do some examples. So if we take n equals 12, we would have our set 1, 2, 3, 4, 5, ... 11. And then I want to know which numbers are relatively prime. So 1 shares, well, what's the definition of relatively prime? So 1 works. What about 2? No. 2. What about 3? No. 4. 5. 6, no. 7, yes. 8, no. 9, no. 10, no. 11, yes. So there are 11. So phi of n, so here, so phi of 12 would be 4. Let's do another example. Let's take n equals 7. So we have 1, 2, 3, 4, 5, 6. What do you think phi of 7 would be? 6. So you're saying every number is relatively prime. What if instead of doing n equals 7, I did n equals 11? So I have 1, 2, so you're getting this really fast. So phi of 11 is 10. So what are you noticing? N minus 1. Okay, is it always n minus 1? When it's prime. So we know that this is going to be n minus 1 if n is prime. And the reason is, well, if 7 is a prime number, then none of the numbers from 1 to 6 can share a factor with 7. So we can compute phi very easily at primes. Then the question is, where else can we compute phi? And it turns out we want to be able to compute it for a general n. Well, that would take us into a lot of group theory, so I'm going to just do it for n that are the product of two distinct primes. And you can do it more generally, but let's just do it for the special case when n is the product of two distinct primes. This would not quite work because this is 2 times 2 times 3. So I want my n to be p times q.
Like 50.
Like, which one?
15?
15, yes. I thought you said 50. I was going, 50. 15 would work. So let's gather some data. So let's take n equals 15.
Distinct primes, like not 25.
Correct. 25 would not work. So I want two distinct primes. So I would have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what would you say here for phi of 15? So let's see. So 1 works. What else works? 2. 3 doesn't work. 4 works. 5 doesn't work. 6 doesn't work. 7 works. 8 works. 9 doesn't. 10 doesn't. 11 does. 12 doesn't. 13 does. And 14 does. 1, 2, 3, 4, 5, 6, 7, 8. So you get phi of 15 is 8. I'm sorry? No.
Phi of 5 times phi of 3.
Ah, so that's one conjecture, is that this is phi of 5 plus phi of 3. I heard another conjecture.
That's the sum of the
Yes.
two distinct primes.
Oh, I'm sorry, I wrote yours, and now I'll write yours. So they unfortunately, do they both work here?
Yeah.
So
What's phi of 5? 4. And what's phi of 3? 2. Okay, so we know this doesn't work. Okay. But 4 times 2 is 8. So we now at least have a conjecture. Okay, fast forward 20 minutes, we've just explored about 13 different choices of products of two primes, and in every case, this worked. So we now believe that this is the answer. That if you have two distinct primes, it's going to be their product.
What's interesting is the number is the same, but it's not the same numbers. Like,
Correct.
Here's a
Right.
Right. So the question is how they mix together.
yeah.
And that becomes a key part of how the encryption works and how they get jumbled. And there's a lot you can say about that, so we're just really skirting the surface, but there is a lot of wonderful stuff there. So let's try to show if,
We got it in general.
so if n equals p times q, and p and q are relatively prime, then phi of p times q is phi of p, phi of q. If you are watching this extremely carefully, you will notice that I didn't say p and q are distinct primes. I just said phi and q are relatively prime numbers. They have no common factor. So these are called multiplicative functions.
That's a generalization.
This
They
is a
don't
generalization.
actually-
Right. We're only going to prove it in the special case when p and q are prime, but it actually holds it a little bit more generality. If you have two numbers that have no common factors, then phi of the product is the product of the p's. What this means is that if you want to understand a complicated number, you can understand it in terms of simpler cases, and you can just build up from that knowledge. We will assume p and q are prime. All right, so we need the numbers 1, 2, 3, dot, 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 p plus 1, dot, 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 q plus 1, dot, 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 all the way up to pq minus 1. This is going to be our set. And we need to figure out how many of these numbers are relatively prime.
Relatively prime to each other, or to
Relatively prime to pq. Yes?
Well, P is a factor of EQ. So anything that is not relatively prime to P is also not relatively prime. Or that is, so yeah, so you're not going to get new things. Like things you could have eliminated with P will not be able to be included for P times Q.
Right.
And the same thing with Q's.
Right. So we know initially all the numbers from 1 to p minus 1 work for the first one, and 1 to q minus 1 work for the second one. Let's assume p is less than q, just one of them has to be smaller than the other. But now the question is, how do they mix together? Because since q is greater than p, some of the things less than or equal to q minus 1 will be multiples of p. So the products are going to, so you could take things that are relatively prime to p and things relatively prime to q and multiply them. That will be fine. But you might miss numbers that aren't the product of either. For instance, I could take a large prime that's greater than p, greater than q, but less than p times q. And that's not going to be a product. So this would find me some numbers, but not all. A lot of times, and this is a really good math principle, rather than solving the question you are asked, sometimes a related question is easier to analyze. So if I want to calculate the probability that I win, if I can calculate the probability I lose, and there's no such thing as a tie, then that's as good as calculating the probability I win. So rather than trying to find the numbers that are relatively prime to p and q, what should we do? Find the ones that are not. So who shares factors? So what's the first number you can think of that shares a factor?
The first number that shares a factor.
With,
Share a factor?
yeah, with p times q. P. And what's your next one?
Q.
Okay, I'll put q down here. After p, what's the next one you would think of? 2p. And then what? And all the way up to? I'll go all the way up to pq. And let's look down here. We have q, 2q. All right, in this, I'm not going to go beyond that with people speaking. And then we go all the way up to pq. So these are all the ones that share a factor. But we've double counted pq. So the numbers that are relatively prime, we have pq numbers. We have to subtract off all of these. How many of these are there? So how many numbers are there in this row? Q numbers. Then we subtract off how many are in this row, which is p numbers. And now what do we have to add back? We have to add back 1 because we subtracted off pq twice. And the reason I wanted to write it like this is because it now factors nicely as to p minus 1 times q minus 1. So if you just expand this out, you'll get pq minus q minus p plus 1. And that is just phi of p, phi of q. So we can count how many numbers are relatively prime to pq. It's just p minus 1, q minus 1. And if you think back to RSA, we had two numbers e and d such that e times d was 1 mod p minus 1, q minus 1. And you can begin to see now where this p minus 1, q minus 1 is coming from.
Sorry, that last thing was that, I thought we were looking at the numbers that weren't.
Right, these are the numbers that share a common factor, and we've double counted this number twice.
Yeah.
So if I want the numbers that are relatively prime, it's how many numbers I have, minus all of these,
Okay.
and then I have to add back the 1. How many of you have seen Indiana Jones and the Raiders of the Lost Ark? You know, where the medallion is burned on the Nazi's hand, but he doesn't have the back side, so they dig in the wrong spot. You know, you have to subtract 1 or add 1 for the Hebrew God who is 1, since we're in Hillel here. Yes?
Another way to think about it, going back to the 15 example.
Yes.
You can think of it as prime factors are 3 and 5.
Right.
So we're going to keep 2/3 of the numbers that aren't multiples of 3.
Okay, so keep
We're
2/3 of them.
4/5 of the numbers that aren't multiples of 5.
Mm-hmm.
Right? So then it's all 15 times 2/3 times 3/5.
So you can look at it as
4/5.
so you can look at it as keeping 2/3 and keeping 4/5. You just want to be careful about where they could overlap. And because p and q are just primes, the only time they will overlap is at the very end. You want to make sure that you are not removing something twice. So if p and q had a factor in common, you would have to be very careful about that argument about removing things because you could remove
I
something.
wasn't removing, I was focusing on keeping.
Okay.
So in a sense, the way I think about it is, it would be p cubed times p minus 1 over p
Right.
times q minus 1 over q. And I get the same thing as that.
Right, but I'm just saying, would your argument still work if these weren't primes, or if they shared a common factor?
No, I need to do it with prime factors.
Right. So again, there's many ways to try to push this forward.
But in that that's kind of like an inclusion exclusion.
This is absolutely an inclusion exclusion.
So when those aren't prime, yeah, but they're relatively prime, you say that will still work?
As long as they're relatively prime, this will still work. But it becomes more involved if they're relatively prime, and since there's no need to do that, it's enough to just do this one case. I'm trying to do the heavy math in the morning and not the afternoon.
Would that be a proof that phi of pq is the...
Yes, if p and q are both prime, because we needed to be able to do this argument here. This is where we're using the primality. So in the special case when they're prime, this is true.
So proof of the special case they're prime.
Correct. The result is true in greater generality. But I'm only proving what we need. Okay, so now the question is, who cares? And so I'm going to show you some interesting applications of this. So I mentioned Fermat's little theorem. So do you remember the dot game we did last time where I could prove to you that player 1 had a winning strategy without being able to construct it? This should bother you, right? Non-constructive proofs exist. I want to know how to do it. Well, sadly, a lot of times in math, we can just prove it can be done. So here's a great result from Fermat's little theorem. Let A be relatively prime to n. Then A to the phi of n is congruent to 1 mod n. All right? Whenever we have something like this, we should do a check. Let's do an interesting case. Let's do n equals 12. So phi of 12 we've said is 4. I need a number that's relatively prime to 12. All right, let's take a equals 1. All right, this is kind of stupid. Then a to the 4th is just 1, so it works. It's really not that impressive if I take a equals 1. So I need a number other than 1 that's relatively prime to 12. What should I try? I'm sorry? 5. So if I take a as 5, then a squared is 25. And what is 25 mod 12? 1. It's 1 mod 12. Well, I want to get up to a to the 4th. I'm going to start off with a squared. I could just do a to the 4th is 625 and worry about how do I reduce 625 mod 12? 625. Oh, sorry, 625. I at least said the right thing. So, crappy cheap markers. So I could calculate a to the 4th. I could then reduce 625 mod 12. But I can actually do it a little bit faster. But if I know a squared is 1 mod 12, a to the 4th is just a squared times a squared, which is the same as 1 times 1, which is just 1 mod 12. This is not a proof, but at least we now have some confidence. Have I given you the fraction division? How to divide 2-digit fractions? Did we do that? No. Oh, this is one of my favorite examples in all of mathematics. So this is a great thing to use with your students. 16 divided by 64 in lowest terms. I'm sorry? 1/4. 19 over 95 in lowest terms. Okay, you guys are fast. 49 over 98 in lowest terms. All right, let's do one more. 12 over 24 in lowest terms. I'm sorry? I get a 4th.
24?
Yeah.
12, 48.
All right, let me show my work. 16 divided by 64, cancel the 6's, get 1/4. 19 over 95, cancel the 9's, get 1/5. 49 over 98, cancel the 9's, get 4/8, which reduces to 1/2. So clearly, since we've checked 3 cases, this must be the way you divide numbers. So 12 over 24 must be 1/4. So I love to use this when I talk to my students about there is no such thing as proof by example. There's proof by exhaustion, where you exhaust every possible case. But just because the pattern persists a couple of times does not mean it will always persist. You start to get more confident as you get more and more examples. And for stuff like this,
There are only about 4 of those.
there's not that many. Oh, absolutely. And the other one I like is the Euler time polynomial. So, consider the function f of n is n squared plus n plus 41. F of 0 is 41 is prime. And in fact, if you keep putting in values of n, you keep getting primes up to 39. Up to f of 39 is also prime. F of 40 is composite. So you can play a game, how long can you generate primes? If you're doing this in a class, what you should do is you should stop around F35. And then if the students explore a little bit further, it's still prime. You give yourself a little bit in the bank.
That's called Euler's.
This is Euler's prime polynomial.
I've seen it with 17 instead of 41.
There's a bunch of different ones you can put in here. And it will give you a prime for those consecutive ones. And so there's a whole theory about when can you play games like this. So I just want to warn you that you have to be careful about examples. I still encourage you to do examples and build intuition, but it's not a proof.
Show kids that. Proof by example is not a great.
No, and that's why I love this fraction.
Does anyone ever use brain pop? Brain pop just is a little quick 2-minute introduction to the concept that I read here. And it's very simple and straightforward, but they show that 3, 4, 5, they plug them into the equation, and they show that it's true. And the next thing he says is, we just proved the Pythagorean theorem. Pause. And like, did they really just prove it? And I make my 8th graders think
Right.
about that. Like, no, they just showed us an example.
Right. And there are certain things where you can have a lot of non-trivial examples, but it's false. And these are very carefully constructed examples. So for instance, for my divisions, I was very careful. So imagine n is a prime p. Then what is phi of n if n is prime? It's n minus 1. So a to the n minus 1 is equal to 1 mod n. This is a way to check if n is prime. So, proof that 6 is composite. All right? Give me a number relatively prime to 6. 5. So let's look at 5 to the 6 minus 1. All right? That's equal to 5 to the 5th. And I want to look at this mod 6. Right? So 3125? So we have 5 to the 5th. It's 3125, and I want to look at mod. Yep, I just want to make sure I do it right. Mod.
When you throw away 3,000, you throw away 120.
And so we're looking at this mod 6. And so we get 5. So if n is prime, by Fermat's little theorem, a to the phi of n is 1 mod n. So I plug in a equals 5, and I see that 5 to the 5th is not 1 mod 6. Therefore, 6 is composite. We have proven that 6 is composite. When you think of a composite number, what do you think of? What property does a composite number have? It has prime factors. I have no idea what the prime factorization of 6 is. I just know that 6 is not prime, because if it was prime, then this would be true. So you could actually prove a number's composite without being able to give a factor. Well, I know it's composite. Oh, you want a factor? No. Now, it turns out that there are certain numbers, these are called Carmichael numbers, such that they are composite, but they always pass this test. It turns out there are far fewer Carmichael numbers than prime numbers. Most numbers that pass this test are prime. And it's possible that a number might pass it to one value of A but not another value of A. So if you try a couple of values of A and it works every single time, you become more and more confident that you found a prime. But it's unfortunately not a proof because there exist infinitely many numbers such that this holds. There are far fewer Carmichael numbers than prime numbers, but there is still the danger.
What's meant by a pseudoprime?
A pseudoprime, I think, is that might be a Carmichael number. It passes this for every A. There's a couple of different ways you can do pseudoprimes based on what your primality test is. Does it always pass your test? Then you have numbers that are probably prime or industrially prime, where they pass this test so many times that the odds that it's composite is like 1 over 10 to the 200. So you're very confident that it's prime, but it may not be. And so for certain things, what you can do is you can do some quick tests to get a candidate. And then there are some slower tests that are guaranteed to work that will tell you if your number is prime or not. But these tests are slow. So what you first do is you do one of the quicker tests to eliminate a bunch of numbers. And then when you have a candidate, then you do the really slow, careful test. All right, so we want to prove Fermat's little theorem. And so the question is how to prove this. We really only need this if n is a prime or product of two distinct primes. We don't need it in general. I'm only going to do the proof in the case when n is prime. As a nice exercise, try to modify my proof for the case when n is a product of two primes. The idea I'm using will work, but I am trying to do the bare minimum we need for RSA. Okay, so here's the proof. So we'll assume n equals p. Yes?
How do you get from the idea that if it holds for a prime, it holds to the product of two distinct primes, which is by definition not a prime?
No, you have to prove that. I'm saying we only need it today in these two cases.
Okay.
So it's really a fact in group theory or abstract algebra about orders of elements in a group. There's a theorem called Lagranges Theorem that really is what's going on here. This is a special case of Lagranges Theorem, and we can prove the special cases we need very elementarily without introducing all this abstract nonsense. And in fact, while it would be useful to have it for the product of two distinct primes, I think I can actually get around that and do a little backdoor trick, which I want to show. Quick question?
We're just trying to remember the
Right, so if you have a group, any subgroup's order divides the order of the whole group. And if you look at the subgroup generated by an individual element, then that's going to be a subgroup itself, so that has to divide. So I am probably the only math professor who has never actually taken abstract algebra. It didn't fit into my schedule. I've taught it multiple times. But, all right, so let's prove it in the special case. And this allows us to use some really nice stuff. And again, I'm trying to take proofs today that emphasize great mathematical thoughts. What is really going on here is we have a finite set of numbers, and we can do a lot with a finite set of numbers. So we have the numbers 1, 2, 3, p minus 2, p minus 1. P is our prime. So n equals P. So I always like to write P for a prime. All right. So now choose a relatively prime to P. Okay? Consider the following set. A, 2A, 3A, dot, 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 P minus 2 times A, and P minus 1 times A. Do we agree these two sets have the same size?
Because there's P minus 1.
P minus 1 elements of both. So the question is, could any two elements of this set be the same? For instance, could, 2A, it's a terrible A. Could 2A equal 7A? And we're looking at this mod P. Well, what would that mean? That would mean 2A equals 7A plus some multiple of P. So if we subtract, we would get 2 minus 7 times A is equal to a multiple of P. Can P divide A? No, they're relatively prime. So that means P must divide 2 minus 7. Well, our numbers range from 1 to P minus 1. The maximum this could be is P minus 2. And the minimum it could be is negative P minus 2. Right? The most extreme this could be is if I choose one of my multiples is P minus 1 and the other multiple is 1, and then the difference would be P minus 2. P is not going to divide P minus 2. The other case is I could choose 1 and P minus 1, and then the difference would then be 2 minus P. And so it can't divide this either. So the only way it could divide is if these two numbers are the same. So these are all distinct mod P. So I'm doing the special case of 2 and 7, but the argument really applies in general. There's one case you might need to worry about. What if P actually equals 2? Well, if P equals 2, then P minus 1 is 1, and I'm just talking about the set of 1. Okay, I'm not really worried about that special set, but you should be careful. There is something I have just done here that is a sleight of hand. It is usually not emphasized, which is a shame. But I have made an implicit assumption that has to be proved painfully. And it's that if I have a prime on the right-hand side, if it divides the right, it divides the left. Well, that's clear because they're equal. And then if a prime divides a product, it has to divide one or the other term, maybe both. That I can't have, if this is 7, part of 7 divides this, and then the rest of it divides that. So we need, if P divides x, y, then P divides x or P divides y. I'm not going to prove that. I will give you a little handout on that afterwards if you're interested. It turns out this is non-trivial to prove. One of the ways it's often proved, or used to prove this, is the Euclidean algorithm. And there was a reason we spent time doing that. It's something that has a lot of consequences to it.
So you're saying you just used that?
I just used it. I didn't highlight it. I didn't emphasize it. I just tried to sneak it in.
Okay.
It's very easy to sneak things in proofs and just have an implicit assumption. It seems reasonable. How many people here have seen sines and cosines? Okay. So, as an aside, all right, 1 minus cosine x times 1 plus cosine x is sine x sine x. Because this is going to be 1 minus cosine squared. Cosine squared plus sine squared is 1, so 1 minus cosine squared is sine squared. So sine of x should either divide 1 plus cosine of x Or no, it doesn't. So this is an example where I can have a factorization, but terms on the right do not have to divide. So this idea that, well, if I have a product, clearly, the question is, what's a prime element? And in abstract algebra group theory, you have lots of discussions as to what does it mean to be a prime element as you generalize. So I'm just trying to give you a sense of a little bit of what's out there and just how easy it is to assume things. We don't need to worry about any of this. So it'll be erased, but we should be at least aware of what we're assuming. Okay, so these two sets are the same, right? When we look at this mod P, when we look at the remainders, they're all the same. And if you want, as a nice exercise, choose P equals 7, A equals 5, and actually just write this down and just do an example. So, do P equals 7, A equals 5. And just see that when you look at everything mod P, it really is the numbers 1 through 6 just rearranged. So if this is the case, if I multiply all of these elements, and I multiply all of these elements, they have to be the same mod P. Right? Because all of these elements are the same as these, just rearranged. So I get 1 times 2 times 3 times P minus 1 is the same as A times 2A times 3A times dot 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 times P minus 1A. Ah, yes, it's always great as a mathematician when you hear something in the audience go, oh. So what do you notice both sides have? Both sides have a P minus 1. What else do both sides have? A 1, a 2, 3. So I can cancel the P minus 1 factorials from both sides. And so we get 1 is congruent to A to the P minus 1 mod P. And so the only difference is that over here I have the mod N on the side of the 1, and here I have the mod on the side of the A. Not a big deal.
Okay, 1 second.
Yep.
So
we did massive cancellation.
why are we saying that they're equal mod P?
Well, because
I saw they're equal in size. I guess
they're equal in size, but we also then just showed that no two numbers on this list are the same.
Okay.
Because they have the same number of elements, since no numbers are the same, it has to be these numbers rewritten.
Oh,
If I had-
all mod P.
Right.
If you had like 5 elements.
If I have 5 elements that are distinct,
Yeah.
and there are only 5 possibilities, then it's got to be those 5 possibilities reordered. If I had infinitely many elements, then it would not be true.
Should there be a mod P on both sides of that equation?
Well, it's enough to just write mod P on one side.
Okay.
And so when you write mod P on one side, it means you're just looking at it on a clock with P hours.
Okay. So since they're both mod P.
So since they're both mod P, same size,
Same set.
So, I mean, just a simple example, if you're mod 7, and you do multiple 2, you got 2, 4, 6, 1, 3, 5.
Correct.
Right.
No, I get it.
Yeah. The order's just shuffled. If you see My Cousin Vinny, it's the identical. My kids got to watch that movie once they passed the profanity test. I would give them a letter, and I would ask them, what letter comes next? And they not only got the words I knew, they got some words they didn't know. Like, oh yeah, that's also a bad word. Yes, okay, yes.
What test is that?
What you learn at school. But so looking at these, since they have the same size, and since everything here is distinct, they have to be these numbers just permuted. And so this product is the same as this product. And so because this is a multiple, these are the same, that means they differ by a multiple of P. I can divide both sides by 2 because 2 is relatively prime to P. I can divide both sides by 3. I can keep playing that game. So you want to make this a little bit rigorous, but you can see now that A to the P minus 1 is 1. My exercise to you is, what if N was a product of 2 primes? Could you make this argument work? Right. We don't need to do that. We need the result, but we don't need to do it. There's a backdoor around that. Okay.
So are you looking at everything having a multiplicative inverse?
So we would be looking at the things with multiplicative inverses. So you would look at your set would be all the numbers relatively prime to P times Q. And then you would play the same game of choosing a number A relatively prime to them and looking at what goes on. It's a very similar proof. So as a nice exercise, do N equals P times Q, 2 distinct primes. See if you can make this work. What's nice here is I can easily write down all the numbers. I can show you explicitly what I'm doing. In the general case, you would say, okay, I've got some numbers, x1, x2, x3, all the way up to x of p minus 1, q minus 1. Okay, any questions so far? So we've actually done a good amount of group theory already. We just haven't used the language they like to use. But what's nice is we've also discovered a test for primality. And it's actually a good test, because to calculate a to a high power, well, we did the method of repeated squaring or fast multiplication last time. We can run this in logarithmic time. It's not hard to calculate a to the phi of n. So this is actually a very fast test. The problem is the test doesn't always work. If the test tells you composite, you can trust it. But it might return, could be prime. And then you try another a, could be prime. At every a you try, you might keep getting could be prime. That's not a proof at the end of the day. And there are such things as Carmichael numbers where you will have these issues. Okay. Any questions on the proof of n is a prime? Okay. So we want the product of two distinct primes. I'm not going to modify this proof. I'm going to look at it a slightly different way.
All right, so we're getting a test for primality.
Yeah, I thought you said we were getting a test. I was supposed to prepare a test for you guys?
This is a test for primality.
This is a test for primality.
And
It's not a... It depends on how you look at it as to whether or not it's a good test or not. For composite number, it will return composite for almost every composite number you put in. But there are a couple of composite numbers called the Carmichael numbers that it will not be able to distinguish from primes.
so we have some false positives.
Well, it doesn't actually say prime. It says probably prime. So it's not quite a false. It depends on if you want to call it a false positive. It doesn't say prime. It says possibly prime. And the more a's you try, the more likely it is to be a real prime. And so it's a huge theory to try to figure out a fast way to determine if a number is prime. We now actually have such an algorithm. It came out in 2002. And it was discovered by an Indian computer scientist and his 2 undergraduates. And when the camera is not rolling, I can tell some backstories about that. We do not have a fast way to factor numbers. Quantum computers open up the possibility of being able to do that. When I say we, I mean what the world knows publicly. I make no claim as to what certain intelligence agencies know or don't know. So it may be the case that fast algorithms to factor numbers exist. If you've seen the movie Sneakers, that's what everything was about, is finding a fast way to factor numbers and crack RSA. All right, so I want to now do RSA. So in RSA, we had public n, which was the product of 2 primes. We had E, so these were public, and private was P, Q, and D with ED congruent to 1 mod P minus 1, Q minus 1. But after this wonderful lecture in the morning, you now know that P minus 1, Q minus 1 is just phi of PQ, or just phi of n. Okay? So this is what we're making public, this is what we're keeping private, and we send a message M relatively prime to PQ. We send M to the E mod PQ, and then we compute M to the E mod PQ to the D mod PQ. And this is supposed to be our original message M. So this is what Bob has, and Alice is able to send a message. Okay, so I'm now going to show you why RSA works. The first thing is we need a D for decrypt such that E times D is 1 mod P minus 1 Q minus 1. Okay, so the first is finding D. Okay, this. So how do we find D? So we start with phi of pq is p minus 1 times q minus 1. Choose E relatively prime to phi of pq. So do you think this is easy or hard to find an E relatively prime to phi of pq? Let's say P and Q are about 10 to the 200. And I want to choose a number between 1 and 10 to the 400 that's relatively prime to P and Q. You know, I probably don't want E to be too small. I want E to be somewhat large. How many numbers have a common factor with PQ? Well, we're looking for the numbers from 1 to PQ. So how many numbers are relatively prime to PQ? So that will give us our probability of success. The number of numbers relatively prime to PQ divided by PQ. So how many numbers are relatively prime to PQ? It's more than just P and Q. We actually have a name for the function that gives us how many numbers are relatively prime. Yeah, right? It's phi of PQ divided by PQ. That's the probability that a randomly chosen number is going to be relatively prime.
Hold on, the probability that a random relatively prime to PQ.
Right. So this is how many numbers are relatively prime to PQ from 1 to PQ. This is how many numbers are at most PQ. Well, this is then going to just be P minus 1 over P times Q minus 1 over Q. So this is 1 minus 1 over P, 1 minus 1 over Q. If P and Q are of size 10 to the 200, this is approximately 1 minus 2 over 10 to the 400. No, 10 to the 200. So if P and Q are of size 10 to the 200, it's approximately 1 minus 2 times 10 to the 200. This is as close to a sure bet as you are going to find. You know,
Minus a tiny number, yeah.
an extremely tiny number.
Right.
So if every subatomic particle in the universe was a universe, and you counted how many subatomic particles you would have, that's far less than 10 to the 200.
So there's a 100% chance that
It's essentially 100. So
is relatively prime to the product.
exactly. So if I just choose a random E, almost surely E will be relatively prime. What would I do if it wasn't? Choose another. What would I do if it isn't?
Go play lottery.
Okay. Within 2 or 3 tries, one try almost surely, I should be fine. This reminds me of the old joke, the probability of a bomb being on a plane is 1 in a million. So a mathematician brings a bomb because he says, well, the probability of 2 bombs on a plane. Okay, so we can choose an E that's relatively prime to phi q very easily. Now, as E and phi of PQ are relatively prime, that implies their GCD is 1. Right? So by the Euclidean algorithm, then we can write, D times E plus F times phi of PQ equals 1. Sure. So because E and phi of PQ are relatively prime, that means the greatest common divisor is 1. If the greatest common divisor wasn't 1, it would be relatively prime. Let's say the greatest common divisor was 5, then 5 would divide both. So because their greatest common divisor is 1, I can now use the Euclidean algorithm. And the Euclidean algorithm says, if you give me your numbers E and phi of PQ, I have some coefficients such that D times E plus F times phi of PQ is 1, is just the greatest common divisor. And we can do this fast. It's very easy to find the D and the F.
This D is different than
No, it's actually going to be this D. And that's why I'm not using the letters A and B here. I'm deliberately using D, and that's why I moved up to F over here to just be alpha.
F is just the multiplier?
F is just the multiplier. It's just the Euclidean algorithm says there's got to be 2 numbers.
So D will be the coefficient.
And D will be the one I need. Right. And the idea is it's easy for us to find D. So it's fast and easy. We'll define both. We're choosing E, and we saw that the probability that we feel is 1 minus about 2 over 10 to the 200.
And we know phi of PQ.
We know phi of PQ.
We know those. It doesn't take long to find D.
Right. So for us, we know E, we know phi of PQ, so we can compute D easily. Now you put yourself in the mindset of the eavesdropper. The eavesdropper only knows N and E. They don't know what phi of PQ is. If they could factor N, then they would know P and Q, they would know P minus 1 and Q minus 1, and then they could compute D trivially. So if you can factor quickly, then it's trivial to get D. We believe factoring is hard because people have tried for centuries without being able to solve it. That does not mean that factoring is hard. It just means that so far no one has publicly come forward with a good, easy way to factor. So the hope is that this is a secure method, that without knowing this extra information, you can't get D easily. So these are often called backdoor systems, that if you have extra information, the problem is trivial. If you don't have that extra information, there's no easy way to do it. And sometimes what you think might be secure turns out not to be secure. And there have been many examples of crypto systems that were thought to be secure, but then somebody finds an attack that does work without that extra bit of information. So we're seeing lots of consequences of the Euclidean algorithm. And when I say, choose a D such that this is true, is it possible to choose such a D? Yes. And we can choose such a D quickly. If it took us 2 years to compute D, that'd be terrible. But this is running at the Euclidean algorithm rate, it's fast. All right, so now we know how to generate everything we need. All we have to do is prove that the decryption of the encrypted message is the original message, and we're done. Yes?
I understand the math better than I understand the concept of the RSA. Is it essentially like the Caesar cipher? I mean, what are we using N for relative to the message?
So what we're doing is we're trying to find a way to encrypt a message so that only a specific person can decrypt it.
No, I understand that. I mean, literally, how are you using
Okay,
RSA to encrypt the message?
So what we're doing is we start off with the message M, and we raise it to the eth power, and then we send its remainder when we divide by PQ. So the thing is, we're not doing it letter by letter. We take the whole message and encrypt the whole thing, and send that whole thing.
So it is a string of
Correct.
many
So if you were to change one letter in your message, then M would change, and in particular M to the E would change greatly.
Okay.
So two messages that differ by 1 digit could be very far apart in being transmitted.
This was the piece
Yes,
I was missing.
yes.
It's like, I got the math over here, I got the message
Yes,
over here.
yes.
That would be analogous to putting it in the lockbox in the pirate problem.
Yes. And in fact, the pirate problem is essentially this.
Right.
Is this an NP complete thing with computer science? Is that, like, right now, it just sounds like it's easy to
Well,
solve,
right
but
now,
not because, so it's, do you understand?
Right. I don't remember exactly where factorization is on the NP scale.
Yeah.
I know like the traveling salesman problem is one of the NP problems, that if you can do that quickly, you can do all these other things.
Right.
I do know that quantum computers are supposed to be able to factor in polynomial time and be very, very fast. And it's usually like polynomial time in the number of digits, which would be like logarithmic time in the size of the number.
So would that negate RSA security?
Yes, absolutely. So in fact, a lot of people have switched from RSA encryption to other systems because of the fear of quantum computers. And you want to switch early.
What's the timeline on those now? Because I've been hearing about them for like...
I've been hearing about them for at least a decade.
Yeah.
And
I remember hearing about them when I went to a conference my
Right.
first year.
And so
like
I don't know, but I know there's some lattice-based systems that people like, and I know there's some elliptic curve-based systems that people like. And what's really lurking in all of these encryption systems is you take a math concept and you try to build an encryption around it where if you don't know some extra information, it's supposed to be hard to solve the problem. Okay, so let's just do the last part. We have to compute M to the E and then raise that to the dth power. and show that that equals the original message when we divide by PQ. And that's all that's left. Okay. So, proof 1. Yeah, we're proving that this works. So I claim that m to the e mod pq to the d mod pq is just m to the ed mod pq. And if you think about what's going on, m to the e mod pq is just m to the e plus some multiple of pq. And then I raise this to the dth power. And when I raise this to the dth power, I'll get the first term is going to be me to the d, and then everything else is going to have at least one of these factors. So everything else is going to be multiple of pq. So the first is that it's enough to just study m to the ed. Okay? Everybody comfortable with that simplification? That just, when I look at the remainder mod pq, well, if I had an extra mpq here, when I raise it to the dth power, the only time I don't see this is when I have this d times. This is just from expanding out, x plus y to the d is x to the d plus d choose 1, x to the d minus 1y plus dot 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 plus y to the n. And every term but the first is going to have a y. So every term but the first is going to have a multiple of PQ. So I just have to calculate m to the ed. Okay. So here we go. Remember, ed is congruent to 1 mod phi of PQ. So that means ed equals 1 plus, say, m PQ. So m to the ed is m to the 1 plus m pq. This is the same as m times m to the m pq. Is the light getting you?
No, I'm good now. No,
Okay.
I was just back and forth. Now I'm good.
Excellent. So I'm just splitting up the multiplication. Well, now I'm just doing lots of laws of exponents. This is just m to the p. Oh, I'm sorry. It's not pq. It's phi of pq. Right. It's supposed to be m times phi of pq. M times phi of pq. M times phi of pq. M to the phi of pq, and then I raise this to the mth power. Okay? So I've just done some algebra. What's great is over here, that's our message. All we need to show is that this thing here is 1 mod PQ. Ah, but that's Fermat's little theorem. If I take any number relatively prime to n and raise it to the phi of n, I get 1 mod n. So by Fermat's little theorem, this thing inside the brackets is 1, and I just raise 1 to the mth power, and it's still going to be 1 mod PQ. So this will just be equal to the message mod PQ by Fermat's little theorem, lowercase l. So this is a nice consequence of Fermat's little theorem. And the key step was over here. We can now just use Fermat's little theorem. So A is equal to M, N is equal to P times Q. So this whole thing here is just 1 mod N. So this is just 1 mod P times Q. So that proves why RSA works. If we had this proof when it works for 2 distinct primes. We unfortunately only proved it for n is a product of, n is just 1 distinct prime. So we have 2 options. One is to prove it for 2 distinct primes, or the other is to try to do a backdoor proof. And so I want to do a backdoor proof. Any questions about this argument here?
M to the ED is M.
No, M to the ED.
Is M mod PQ.
So M to the ED is M to the 1 plus a multiple of
You just showed
PQ.
it's
We just showed it's equal to m mod pq, correct. So, and m was the original message. It's the original message. So Alice starts off with some message m. She raises it to the e. She encrypts it with the publicly available e. And she sends m to the e mod pq. Bob receives that and raises what he receives to the dth power. And when he computes it to the dth power, he gets back m. And it's believed that if you don't know what p and q are, if you just know what n and e are, you have no easy way of figuring out what d is. You have no easy way, even if you intercept multiple messages, there's no trick to get them.
If you're the owner of D,
then you can read it.
You're all set.
Right. And we talked last time about how you can use, if Alice has her own encryption scheme, how she can sign her message and bury that inside the message so Bob can verify the identity. All right. So that was proof 1. I wanted to now do proof 2 of the same thing, because I don't want to use the proof for the product of 2 distinct primes. It's not horrible to modify what we did for 1 prime for 2 primes, but I really wanted to see how much can we do with the bare minimum. So that if you want to try to do this with students, what is the bare minimum amount that you need to develop? So proof 2 is going to be very similar. So proof 2.
Again, we're proving that m to the e.
Yes. So proof 2, we still have ed is congruent to 1 mod p minus 1 q minus 1. So that means ed is 1 plus some multiple p minus 1 q minus 1. And what I'm going to do here is it's the trick of switching primes. I'm going to first look at the message, encrypt it, decrypt it, and I'm going to look at that mod p. Then I'm going to look at it mod q. So let's look at m to the ed mod p. Well, this is going to be m to the 1 plus m p minus 1 q minus 1. I'm just putting in what ed is. Right? So I can write this again as it's m to the 1 times m to the m p minus 1 q minus 1. And this is the same as m times m to the p minus 1 to the m, it's a terrible m to the q minus 1. And now you can see the beauty of the trick. What do we know about m to the p minus 1? P is a prime. So we can use Fermat's little theorem in the special case when n is a prime. And so what do we know about m to the p minus 1? It's just 1 mod p. So this whole thing is just going to equal m mod p. We wanted to show it equals the message mod pq. We showed it equals the message mod p. Right. Something at least. And now if we look at m to the ed mod q, what do we get? M mod q. All right, so in the interest of space, I'm going to kill all of this, and let's just recap. So I have some number. I have some number x, and I know x mod p is let's go back a little bit. We had m to the p minus 1 to the m q minus 1 is congruent to 1 mod p. And we have m to the q minus 1 to the m p minus 1 is congruent to 1 mod q. So what do you think this number is, m to the m p minus 1 q minus 1. What do you think that's congruent to mod pq? We know it's 1 mod p. We know it's 1 mod q. What do you think it is mod pq? What would you guess? 1. And if it is 1, then we're done. That's what we want to show. So by using Fermat's little theorem, we got these two lines. So now here's the question. If x is equal to 1 mod p and x equals 1 mod q, so let's think about what does it mean for x to be 1 mod p. So x equals 1 mod p, so x is 1. What's the next possibility could be? 1 plus p. What's the next possibility? 2 plus p. No, 1 side, yes. 1 plus 2p. So it's 1 plus multiple p. And now we know x is congruent to 1 mod q. So x is 1, 1 plus q, 1 plus 2q. And it's got to be equal to both of those.
Only way to be equal to both of those if it's 1 mod pq.
Well, so clearly if it's 1 mod pq, it's going to work for both.
Yeah.
So let's say it's 1 plus ap equals 1 plus bq. So then we can subtract the 1s, and we get ap equals bq. So using the fact that a prime, if it divides a product, has to divide at least one of the factors, can p divide q? No. So p divides b, and q divides a. So now we know a is some multiple, let's call it a m sub q, and b is some multiple of q, and b is some multiple of p. So since a is a multiple of q, we get 1 plus ap is equal to 1 plus mq pq. And that proves that it is congruent to 1 mod pq. So we actually didn't need the stronger version of Fermat's little theorem. It would have been easier if we had that, but I like this idea of switching primes. We analyze it first with respect to the prime p, then we analyze it with respect to the prime q, and when we put them together, we see that it has to be 1 mod pq. And this proves why RSA works. So now we know that this number here is 1 mod pq, and everything is fine. So any questions on this part? So this is the most mathematical of the lecture today. You know, get it done with early in the morning.
I want to see a specific example. Like say we're in mod 77, right? P is 7, Q is 11. Can we find our E and D and all of this stuff and make it work?
Well, so that would just be going through the Euclidean algorithm. So if you wanted to see something like that, so you wanted 77. All right, so we take P equals 7, Q equals 11, and we'll take a better marker. All right, and so what do you want to take E to be? You need some number of relatively prime 5? You want something higher?
Are we doing powers here or no?
Well, we want to, you need to
Our
give,
message can be something else.
Yeah. Right, so what do you want for E?
Sure,
5, or do you want a larger number, like maybe 63? To 63. So it doesn't look. All right, and we want find D such that ED is congruent to 1 mod. So P minus 1, Q minus 1. So P minus 1 is 6, Q minus 1 is 10, mod 60. Okay? So the first thing is E relatively prime to 60? Yes or no?
No, they share 3.
Yeah, they share 3. So if we tried to find a D, we would fail. So we have to change our E. And again, if you chose P and Q to be real big primes, this would almost surely not happen. But because our primes are 7 and 11, these are dinky small little primes. I mean, this is barely a 2-digit prime, right? It's quite likely that you will have a collision. So we have to try a different value here. Let's try 61. Well, let's go 43. I don't want to choose too small of a number. But now I'm choosing E to be prime. So because I chose E to be prime, I know it's going to be relatively prime to 60.
Right.
Right? You can't have a common factor. So now, is E relatively prime to 60? Yes. So now I play the Euclidean algorithm game. So I've got x equals 43, y equals 60. So I write 60 as 1 times 43 plus 17. Yes. Then I write 43 as how many 17s? 2 17s would be 34 plus 9. And then I write 17 as 1 9 plus 8. And then I would write 9 as 1 8 plus 1. And if I went one step further, I would have 8 is 8 1s plus 0. And so I've now gone through, and now I can use this to get my numbers such that, you know, ax plus by equals 1. So I just go through things very carefully, and I start substituting. So here are my numbers, 1, 8, 9, 17, 43, run all the way up to 60. So over here, I get 1 is equal to 9 plus 8. Minus 8. So I just got a proof of Fermat's last theorem to referee. Actually, the author claimed to prove even more than Fermat's last theorem. But that was just a subset of what he proved. Everything was right except for one line where he put a plus sign where there was a minus sign. But you could tell before you even read it that there was no hope that this would work because he's just doing algebraic manipulations. And if the algebra is done correctly, it's going to reduce to a tautology x equals x. And I've tried to explain to him that the method is fundamentally flawed. So he's now tried 4 times. I admire his perseverance, but... All right, so 9 minus 8 is 1. Now we can represent 9 as 17 minus 8. So this is the same as 1 equals 17 minus 8 minus 8. Right? I'm just substituting in for 9 as 17 minus 8. Wait, do I want to do it the other way? No, I want to do it the other way. I want to substitute as 8 is 17 minus 9. Sorry. Because these are the ones that are always isolated and I can solve for the others. I can write 8 in terms of 17 and 9. I can write 9 in terms of 43 and 17. So now I get 1 is equal to 9 minus 8, but 8 is 17 minus 9. So I now have 1 is equal to 2 times 9 minus 17. All right, so now I've used this line. So now I come up to here. I can write 9 in terms of 43 minus 17.
43 minus 2, 17.
Right, so it's going to be 2 times 43 minus 2 times 17 minus 17. So I get 2 times 43 minus 4 minus 5 times 17. Now I come up over here, I have 17, I can write as 60 minus 43. So I get 1 is equal to 2 times 43 minus 5, and 17 is going to be 60 minus 43. So I get 1 is equal to, I've got a minus, and a minus is a plus 5, so it's going to be 7 times 43. And then I'm going to be minus 5 times 60. So this is going to be 300, and this will be 301. And so what should D equal? The coefficient of 43, which is 7. And so we were able to find D. And this is the power of the Euclidean algorithm, is we are able to get D without that much trouble. You just go all the way down, and then you just unwind. So it's phenomenal how quickly this works. And this is the only reason why you can actually do RSA in real life, is if these steps took a long time to do, it wouldn't be practical to use. But because these can be run quickly, and what's nice about this is, if you're teaching 8th grade mathematics, is there really much here beyond 8th grade mathematics? No. No. The difficulty is how much time it would take.
Yeah. Very good.
And given tendencies to have statewide exams and the pressures put on those statewide exams, you then have to do calculations. How much time is it worth spending on a topic that might excite a kid versus building up algebraic proficiency where you have no idea why you're building up this algebraic proficiency. And so if you could do something like this, if you can pull out some units of this, and then later we're going to be doing error correcting and error detecting.
Okay, so we still have to do some message to the 43rd power.
Right.
And then raise it to the 7th and get our message back.
Right. Right, so if we wanted to do that, so we need to take a message that's relatively prime to 77. Okay, so we find D equals 17, as it equals 7. So I'm not going to go through all the details, but now if you have a message, it's not so bad. All right, so now say the message is 13. So we want to send 13. Note 13 is relatively prime to 77.
That was going to be my question. Did you choose 13 because it's prime?
Yes. We could choose something else that's not prime,
Yeah.
but I've just got to avoid 7 and 11, so if I chose 15,
An even number would work, right?
not necessarily, if I chose 14, that would not work.
Oh.
But I could do 2 times 3 times 5, which is 30. So I can take 30 as my message, and then all I have to do is erase the 1 and put a 0 there. Although then the 30, like that. So now it's spaced out nicely. So 30 relatively prime to 77.
Okay.
So I want to compute 30 raised to the 43rd power mod 77. But 43, let's look at powers of 2. We have 1, 2, 4, 8, 16, 32. So it's going to be 1 times 32, and when I subtract that, I'm going to have 11. So I have no 16s, plus 1 times 8, so now I have a 3, plus 1 times 2, plus 1 times 1. So 30 to the 43 is really 30 to the 32 times 30 to the 8 times 30 squared times 30 to the first, mod 77. So now we just use repeated squaring. What is 30 to the first mod 77? 30. Not a big deal. 30 squared, so I'm going to just use my computer. And we're doing mod 77. So it's going to be 53. Then we have to do to the 8th power. So we have 30 to the 8th, and I get 60. And then we have to the 32nd power.
You must have a mod function.
Yes, I have mathematics open with the mod function right there, so that I can do this very fast. Or if you go to Wolfram Alpha, Wolfram Alpha is a great site. Or you could just do the algebra in your head. I mean, really, you're only raising 30 to the 30th. But really, the way you how would you calculate 30 to the 8th? Well, we know 30 squared is 53. So 30 to the 4th would be 53 squared. And then once we have that, then we would square that again. We'd get 30 to the 8th. So that's 60. Now we square that. That would get us 30 to the 16th is 60 squared. So by using repeated squaring, it's not bad. That's really how I'm calculating all of these. So now we just have to multiply all of those. So it's mod.
You can also bring the size of the numbers down by making 60 into like -17 mod 7.
You could, but for some of these things, you're going to spend more time doing that than to actually do the calculations. Or you can also multiply things in pairs. So this ends up as it equals 72 mod 77. So now we need to compute 72. What power do we raise 72 to?
7.
To the 7. Mod 77. Well, 7 is actually very nice in binary.
It's going to be the first square root of 4.
Right. So one thing you could do is you could actually calculate maybe 72 to the 8th and then divide by 2. Or you could just write it as, 72 to the 4th, 72 squared, 72 to the 1st. And so I'm going to my computer to calculate this. I really shouldn't have to do this, right? What should I be getting?
Obviously, you should be getting 30.
I should be getting 30. And we do get 30.
Make sure it's 30.
Yes. And it did come out to 30, so everything is good.
Cool.
So this would be how you would actually implement RSA. It's not that bad. And again, in the real world, you would never do the multiplication. The computer would do it.
Is there a way of seeing ahead of time that 30 squared and 30 to the 37?
The 30 squared is 53, or?
Because you have 53 also for 30 to the 37. Do you have noticed that those would have been 30
Oh.
squared and 30 to the same? Or is that coincidental? Just strikes me as funny.
Well, what this has to be is, it's got to do with the order of the element. So, p minus 1, q minus 1 is 60. 32 and 30 differ by, 32 and 2 differ by 30. 30 is half of 60. So we know that 30 to the 60 is congruent to 1 mod 77. So that means 30 to the 30 is congruent to either plus or minus 1 mod 77. And it turns out it happens to be the case where it's 1 this time and not. But that's why it was nice in this case.
30 to the 32 is 30 to the 30th times 30 squared.
Correct.
Okay.
And 30 to the 30, and again, this is where it's annoying because we have the same number up top and down below. That's just a coincidence.
Yeah.
This is one of the problems of using small numbers. When you have your classes, you need to work hard to make sure that your numbers are not too generic, because you don't want to have something appearing in 2 different places and cause confusion. So this is how you would implement RSA. And again, I really think that this can be done without too much trouble at the 8th grade level. I'm going to be trying with 4th to 6th graders after school at Williamstown Elementary soon. So it will be a subset of the 4th to 6th graders.
Those who are interested in this.
Those who are interested. So to scare people, it says that there will be homework if you come to these. To scare people, yes. Well, we have on the order of maybe 450 people in our elementary school, and we had maybe 60 plus 4th, 5th, and 6th graders coming to math club after school. And it's great that there are that many people that are interested. Because it's recording, I will just leave it at that. But I don't want to try to do RSA encryption with 60 people from 4th to 6th grade. I want a small number of people. But there's a lot of really good algebra and number theory that you can highlight with this. There's also some basic coding. And you can go to Wolfram Alpha, a lot of sites, to just get some familiarity with how do you compute these things. Or you could use Excel spreadsheets. Excel has a mod function. And if you do repeated squaring, it's not bad. This also allows you to talk about the advantages of different bases. Why do we use base 10? Well, we have 10 fingers. Right? Base 2 is much better for a lot of these computations, and you can see the efficiencies. For some things, base 3 is actually better than base 2. To prove that, I need calculus. But if you look at 2 and 3 on the number line, anybody know any famous numbers between 2 and 3? E. And what is E?
So it's 2.7182. So that's closer to
Because E is closer to 3 than 2, it turns out base 3 is better for disk storage than base 2.
Wow. Just because it goes to.
Yes. So there's you need a little bit of calculus for that. I can send you some stuff on this. It's a great calculus problem. It is an optimization problem. And it comes out with certain derivatives, and the best thing to do is to basically do things every eth. Well, since you can't do things every eth, you have to do every second or every third.
The question about the 30 to the 43rd is the reason you did you broke it into those powers is because 30 to the 43rd is too big to deal with?
Right. I would never want to compute 30 to the 43rd.
Yeah, you want to mod it out.
But the other thing is,
Mod it out first,
right,
and
is
the
we
numbers
saw fast multiplication that if we break it up like this,
I mean, like I could type in 30 to the 43rd, but it's just too big. Is that right?
Yeah.
for your calculator, yes.
Yep.
And remember, these numbers in practice are going to be of size 10 to the 200. So if they're too bad already,
Yeah, so you break it down and then it's.
you don't want to do 10 to the 200 multiplications.
Right.
The only way that this can be done.
Okay.
All right, well, here. I'll end briefly with why E is closer to 3 than 2 and why base 3 is. So I won't do the full proof, but I'll do a little bit to give you some sense.
Why is this 3? It's pretty obvious.
Well, first of all, you need a definition of E. Right? So I'm not going to do everything in full. So here's a fun project, or puzzle. So I want to write 100 as a sum of numbers. Each number is greater than or equal to 1 and is an integer. And I want to maximize their product. And so more generally, rather than doing 100, I could just do some number s. The reason I have to say I want the numbers to be greater than or equal to 1 is, well, if I could allow negative numbers, I could do negative 100, negative 100, 200, which compensates those. And these would be, and I can make the product as large as I want it. So if I don't assume that a is greater than or equal to 1, okay, clearly absurd. I don't want any of the a's to be 0. Would I ever have an a that equals 1? For whichever decomposition has the largest product. There's no point in multiplying by 1. So I know that 2 is less than or equal to each number. What if one of my numbers was 10? I could replace 10 with 8 plus 2. And what's the product of 8 plus 2? 16. That beats 10. If I had 5, I could replace that with 3 plus 2. 3 plus 2 gives me a product of 6. What if I had 4?
Let's just say, 2 times
2
2.
times 2 is, I'm indifferent, but let's replace 4. So if I have 3, I can't do this. So I know my numbers are between 2 and 3. I can only use 2s and 3s. Which would you rather have, a lot of 2s or a lot of 3s? I'd rather have a lot of 3s. But the 3s are more expensive than the 2s. So you have a trade-off between 2s and 3s. How many 2s are equivalent to 3s?
1.5.
Okay.
You should do 6 because
So,
squared is 9 and 2 cubed is 8.
right. So you said 1.5, so equivalent to that, 3 2s is the same as 2 3s for the sum. Yes. And so this product is 9, and this product is 8. And so you would, whenever you have 3 2s, you would always replace it with 2 3s. You then need to prove that that the maximum exists. That's some advanced real analysis. But this tells you want to use more 3s. And I'll send you a paper on base 3 where essentially this problem is related to you can store more information with base 3 than base 2. But for binary search and whatnot, base 2 is far easier to work with. But if you just care about storing information, when my father was working in high tech, they invented read-only memory. This was write-only memory. The data is there. I think they nicknamed the project Black Hole. All right, so I think this is a... Right, but you can still access the information from the CD. Right. Yes, right. This was the information is there. The information has been preserved. So if you are legally required to store information, you can say you have fulfilled the legal requirement. The information was written down.
Yeah, maybe. Maybe a judge that's on his first day on the job might find that.
I don't know. Some judges have thrown out a lot of stuff recently. All right, so
that's true. Who's hiring
the
now?
crypto bean problem about the pirates was really the same as the RSA stuff. So we had the two ships. We had two people, and we had the ship going back and forth. We had one person on this island. We had another person on this island. And the idea is you start off with the box, you put in the ring, and the first person locks it. Then you send it over, and then the second person locks it. So lock 2, lock 1. Pirates carry. Now you send it back, and now person 1 removes their lock.
Can we use A and B instead of locks 1 and 2?
Sure. So lock B, and lock A. And now only lock A is here, and now the person can just remove lock A and can see the ring.
Remind me of the chicken and the fox problem with the river. Totally remind me of that problem.
Oh, in terms of
You have to carry
carrying them over and you don't want to be eaten?
Yeah.
It's extra trips.
The
Right.
extra trip. That's where I went and then.
Right. So it's very similar. So at no point in time can the pirates look at it because it's always encrypted. And each person is slowly removing this stuff at the right way. So there's lots of different variants of this. But it's a way for two people to exchange a secret in a noisy medium, in a place where they can be overheard. So the first real success on this was the Diffie-Hellman algorithm. And they sometimes phrase it in terms of colorings with paint. There's lots of different ways of doing it. You need a way for two people to agree upon a secret in public with people over here. And so sometimes people provide some information. And then there are ways where Alice provides her information, Bob provides his information, and then the two of them can send information back and forth and agree upon a secret number that only they will know.
Is that like a one-time key then?
It's like a one-time key that they can then use to communicate.
Right, that's the private key.
That's right. All right, so I think this is a good place to stop for like a 5-minute break.